Hello everyone. Today we'll be introducing to the course Signals and System. Before we begin any course, it is essential to understand the significance of introducing this course into the curriculum. For this, we'll first look at the course outcomes. At the end of the course, you will be able to get acquainted with various type of signals and systems. Represent signals mathematically. You'll be able to learn different signal operations. Compute different response for the given input signal. Analyze various signals in time domain and frequency domain by using different transform techniques. Now let us look into the course. The course title has two terms, signals and system. We'll first look at each of these terms separately. We'll understand signals, we'll understand systems separately. Understanding these terms will help us to understand the overall course, signals and system. Let us look at the first term, signals. What comes to your mind with the word signal? If I guess, yes, various waveforms starts to visualize in your mind. And the very first commonly used signal that comes to our mind is the sinusoidal signal. Why? Because it's the most common and basic signal that we often work with. There are various other signals also that pop up into our mind. It may be an exponential signal, it may be a damped signal. So signal is something that we visualize in the form of a waveform. Now let me ask you, what are the examples of signals? So let us look at a few examples. I've categorized these examples into different categories. Let us look at the Delhi live signals. So we are all surrounded with radio signals. It includes AM signal, FM signal. We have television signals. We have computer signals, speed signal. We have music signal. All these are examples of signals. If I go into the biomedical engineering, we have EEG and ECG signals. Human sensory signals like taste, touch, hearing, and vision are also forms of signals. Measurement of physical quantities like temperature, pressure, humidity are also different types of signals. Basic electrical signals that you are much acquainted with, voltage and current signals. The stock market index is also a type of signal. With all these examples, can we frame a definition for signal? Signal is generally applied to something that conveys information. So signal means something that gives us information from one point to another point. Let us go back to these examples and understand the definition. If I talk about speed signal, the moment you hear some speed signal, we get some signals and we start to interpret the speech. And that's why speed signal is something that conveys information. Music. When we hear the music, we respond. So, music is a signal that conveys information. Taste. When we eat something, we get signals that reach to our brain and we interpret the taste, and hence taste is a signal. Touch, hearing, vision, All these give some signals to our brain, and hence all these falls under the category of signals. Temperature, variation in the temperature. If we look at the graph of a temperature, variation in the temperature over a day, we understand, we interpret, that gives us a signal, and hence temperature measurement could be said as a signal. Voltage, variation in the voltage, variation in the current, right? All these gives us a kind of signal. So basically, signal is something that conveys information. But now let us look at more technical definition of a signal, a more systematic definition of signal, we could say. So signal is a function of one or more independent variables that conveys information. So the new term that we have added into the definition now is independent variables. What do we understand by independent variables? So the examples of independent variables are time, space, or any other observation variable. So these independent variables could be understood with some examples. How do we name the signal using these independent variables? So if I say my signal is f of t, so here t is my independent variable and the signal f is dependent variable. So here signal f depends or varies with respect to independent variable time. If I say a signal s is a function of two independent variables x and y. So here x and y indicates independent variable, s is dependent variable. So s is the signal which is a function of independent variables x and y. So this is how we represent the signals, and hence the definition of the signal includes the word one or more independent variables. We represent signals with these independent variables. Let us understand how the dimensionality of the signal is seen. The dimensionality definitely depends on the number of independent variables used. So one dimensional signal is one in which there is only one independent variable. A multi-dimensional signal is one which has more than one independent variable. So let us understand this with some examples. If I take a voltage signal, how do we represent voltage? We represent voltage as a function of time t. Can have a graphical representation of your voltage. So this is my voltage signal. You call this to be V of t. You are measuring it with respect to time t. So here the measurement is dependent on the independent variable time t. There's only one independent variable involved here, and hence voltage is a one-dimensional signal. Let us look at another example. Let us take image. Right? Suppose this is a particular image. Right? Let me draw something for you. Let us say this is an image. How would you represent this image? So this image, let me say the signal is represented as I, is a function of two independent variables x and y. So what is x and what is y? So x is the horizontal axis, y represents the vertical axis, and any point of the image is to be represented with the two variables x and y. So what this x and y indicates, the pixel of the image is, the brightness of the pixel of the image is given by the variables x and y. So I need two variables in this case to define the signal to represent the image, and hence image becomes a two-dimensional signal. Let us look at one example of three-dimensional signal. Let me talk about representing the signal in a space. So if I'm representing any particular, if I'm talking about any particular point in space, how do I represent this particular point? So this particular point needs to be defined with three variables x, y, and z. And hence, as three variables are involved, this becomes a three-dimensional signal. Right? So the number of independent variables decide the signal dimensionality. So 1D signals basically involve one independent variable. Two-dimensional signals involve two independent variables, and so on. So whenever we define any signal is defined as a function of some independent variables. Now let us take an example and let us represent a signal mathematically with some example. Let us take a speed signal. How do we represent a speed signal mathematically? So speed signal, let us consider a speed signal for this. Right. So let me say this is a speed signal recorded for some instant of time. Let me call the speed signal as s of t. My independent variable is time t, recorded over maybe, let's say, 0 to around 50 seconds. Now when I am interested to put this signal mathematically, we know signal involves different amplitudes, signal involves different frequencies. Hence, representing entire signal by a single mathematical equation is a very complex thing. Hence, speed signals are basically segmented into smaller sections. So we segment these signals into smaller parts. And each segment now could be said is part, it's like a stationary signal, and hence the mathematical representation can be much more accurate. So let us now try to write the mathematical equation for a single segment. So we could say this particular segment of signal has some set of amplitudes and some set of frequencies. So how do we represent it? Let me say my speed signal s of t has some set of amplitude, say ai, and it has some set of frequencies, let me say some fi's, let me say theta is the phase here, and these set of amplitudes and set of frequencies are k. You could say now using a single equation I can now formulate all the segments of the speed signal. So AIs indicate the amplitudes, FIs indicate the different frequencies involved in the speed signal. So this way we can represent any signal mathematically. So summarizing here, we can say that any signal can be mathematically represented. So let me make you recall, you have already studied the subject called analog communication, wherein you studied amplitude modulation, you studied frequency modulation. Do you remember how you had modeled the equation for AM, how you had modeled the signal equation for FM, right? And that's why any signal that you take can be mathematically represented, right? This is very, very important to understand system. So let us now move on to system. So systems, what is the role of system? System process the signals. So the role of system is to operate on the signals. What is the intention of the system? The intention of the system is to obtain a modified form of the input signal. So system is something, you can say right now it's a black box. What it does we don't know, right? And it takes certain input signals, does certain operations on it, and generates an output signal. You could say the output signal is modified or transformed version of original signal. What are the examples of this of systems? So I have listed certain examples which you have worked out, right? You have designed some amplifiers. So what do? You take the input signal and obtain a modified form or amplified form of input signal. So your amplifier definitely is a system. Why? Because it has modified your input signal and to generate a new form of output signal. Filters. You have designed so many filters, a low pass filter, a high pass filter. Right? What do? They take a certain set of input and give you a modified form of output. So filters are nothing but a system. Clippers, clampers that you have designed, all these are systems because they give you a modified form of input signal. Right? So systems are basically designed to obtain the desired output signal. As per the need of what you need at the output end, you design your system. Hence, when we design the system, we should understand the characteristics of the input signal. Hence, mathematical representation of the input signal helps us to design the system because we can identify what are the different characteristics to be modified to obtain the output signal. Hence, mathematical representation of input signal is a very important characteristics of the signal. It helps you to design and get the desired output signal. It helps in fact to design your systems. Now, let us understand the broad category of signals. Signals are basically categorized into continuous time signals and discrete time signals. So let us understand CT and DT signals. Look at these two waveforms to help us understand the signals. The first waveform is CT signal, the other is for a DT signal. Putting these side by side helps us to compare and quickly understand what is a CT signal, how would I define a CT signal, what is a DT signal, and how is it different from CT signal. So continuous time signals, the name itself tells us continuous time. So what is continuous here? Is it the time or is it the magnitude of the signal? Continuous signals are one which are present for all instants of time. The measurement of the variable is present for all instants of time. So you could see here I have a signal which is present from maybe 0 to around 30 units. So around this particular time period the signal is present for all the values of the time, and hence we call such a signal to be a continuous time signal. And what is discrete time signals? You could see here the word discrete. It is associated with time. So what is discrete is the time. What is continuous is time. You are measuring for all instants of time. Whereas in discrete time signal, you are measuring only for discrete instants of time. So here the measurement is done for discrete instants of time. So these discrete instants of time are labeled as 0th instant, instant 1, instant 2, instant 3. It depends on what are the units of your what are the time instants of these. Maybe it is after every 1 second, after every 2 seconds. It depends on the measurement. So here the measurement is not done for all instants of time, and hence it is called as a discrete time signal. So the recordings are done at uniform intervals of time. Could say here at 0 the instant of measurement had a magnitude of around 2.5. At instant 1 the signal had a measurement of unit 3. At instant 2 it is around 1. Right? So a discrete time signal is a signal which is measured at discrete instants of time. But what is very essential here, that these discrete times are at equal instants of time. Whereas in continuous time signal, these signals are measured at continuous at all instants of time. Right? We know these values at all instants of time, whereas in discrete time signal we can't predict what is the value of the signal in between this time instant. Whereas in case of CT signal we are quite definite and sure what is the value of the signal for all instants of measuring time. So this is basically a CT signal and this is a DT signal. I hope this particular example has given you a clear insight about the first category of the signal, CT signal, and discrete time signal. And let us look at examples of each. So what is example of a CT signal? So for this I have taken example of ECG signal. Right? So how is an ECG signal? You could see here. It is recording the movement, the variations in the heart rate of the patient. Right? So you could see here the heart works for all instants of time, and hence the signal is present for all the instants of time. Let us take EEG signal. Right? It's a brain signal. Right? So brain, when it is measured, you could see the signal is present for all instants of time. The brain is working for all instants of time. The signal that is captured is present for all instants of time. So these are examples of CT signals. Let us go to an example of DT signal. You could see here DT signal itself tells us that the measurements are not done for all instants of time, whereas the measurements are done at some discrete instants of time. So here I have taken an example of measuring population of certain countries. So is it possible for us to measure the population for all instants of time? No. It is done maybe on a yearly basis or an annual basis, right? So these are discrete instants of measurement and hence it falls under the category of DT signal. Here is another example. Visitors visiting a particular park. So it's not possible for us to keep the measurement for all instants of time. If I'm measuring it for over a period of year, it's a completely impossible task to do the measurements, and it's neither required. And such type of signals need not be measured for all instants of time, and hence these are measured at discrete instants of time, and hence it falls under the category of a discrete time signal. If I look at another average rainfall over a period of several months, it falls under the category of discrete measurements. We do the measurements at certain discrete instants of time. Right? Similarly, here is another example. So, with these two examples, we have a clear insight of when to go for a CT signal and when there is a need to go for a DT type of signals. So CT signals are signals wherein we need to know the value of the signal for all instants of time. It is essential to get the value of the signal. It's not when the patient is in the ICU, you cannot miss a particular single instant of the time under which and over the period for which the patient is under observation, right? So here the signal is measured for all instants of time, and this could be under the category of CT signal. whereas DT signals are when it is essential to measure the recordings at only certain instants of time, and hence the category becomes a DT signal. So before we stop today's session, stop the introduction session, I want to highlight here certain aspects of the course. As we have just seen, we have one-dimensional signal, we have two, three, or we could say multi-dimensional signal. But in the course, we'll be restricting our studies to only a single dimensional signal. So we'll be using the signals which are only functions of time, and they're all 1D signals. For example, we'll say signal f of t, we'll be using signal s of t, and so on. So whatever signals we'll be using, they're all one-dimensional signal involving only one independent variable, and all the independent variables that we'll be using, they're all functions of time only. So it's my observation that when we are using only time signals, students get a perspective that is time the only independent variable? No. Right? We have just seen we could have two-dimensional signal, three-dimensional signal in which the independent variables are other than time. Right? So please don't create the perspective that the course as the course restricts to only one-dimensional signal, all the signals are only a function of time. No, that's not true. So what notations we'll be using? So throughout, for continuous time signal, we'll be using the notations wherein the independent variable is mentioned with a lowercase t with a parenthesis and the name of the signal. So this is the notation we'll be using throughout the course for representing CT signal. And for DT signal, we'll be using the independent variable as n with the square brackets and the name of the signals. Maybe the name of the signal is P. Right? So we'll be using square brackets. For DT signal, we'll be using parentheses, circular brackets for CT signal. So these notations is what we'll be following throughout the course. Why do I emphasize here on the notations is because many books refer to different notations. And so I want to highlight it here so that you don't get confused when you are reading the books. So throughout the course, we'll be following these notations to understand the signals. So thank you. In the next lecture, we'll be going into more details of CT and DT signals, and then we'll look at some basic signals.